Hey guys, I'm just going to go over a couple of the problems that we did in class just in case anybody needs a refresher. So in this particular problem we had, it's set up very similar to a free response question. You have the balanced reaction given and you have experimental data so that we can determine the answers to these particular questions. Now remember that the rate constant and the order of the reactions must be determined with experimental data. So that's the reason why they gave us this table. So part A says that we need to determine the order of the reaction for each reactant. So we're going to do that with respect to nitrogen monoxide and to oxygen. But before we do that, let's go ahead and write the rate law expression. So in that case, the rate is going to equal the rate constant K times our concentration of our first reactant, which is nitrogen monoxide, raised to some reaction order which we'll determine through the experiment, and then that's going to be multiplied times the oxygen concentration raised to whatever reaction order that is, which we'll determine. So now that we have this set up, we're going to determine the order of the reaction. So for nitrogen monoxide, we want to first look at this part of the table and determine which two experiments have concentrations for nitrogen monoxide that change while the concentration of oxygen is held constant. And that's important because we want to see how the rate is affected by nitrogen monoxide and not the oxygen. So if we look at experiment 1 and experiment 2, we can see that oxygen is constant while nitrogen monoxide changes. So in order to find that order of that reaction, we're going to look at, and I'm going to write on the left side, but we're going to look at how the rate of experiment 2 is changing as a ratio to the rate in experiment 1, and we're going to set that equal to the concentration of nitrogen monoxide in experiment 2 divided by the concentration of nitrogen monoxide in experiment 1. We're also going to be solving for whatever this exponent would be, and that's going to equal what this order is over here. So that's really what we're solving for. So the reason why, in case you're wondering, the reason why we're doing experiment 2 in the numerator and experiment 1 in the denominator is because the concentration is going to be larger in experiment 2 versus experiment 1. So this is going to help us to be able to do the math a little bit easier. Okay, so next what we're going to do is we are going to substitute in for the rate in reaction 2. We're going to substitute the value 0.02, and then we're going to divide that by 0.01. Okay, and then the concentration of nitrogen monoxide, that is what we just did. Okay. Alright, so what we're going to do is we're going to substitute the rate from experiment 2, so that's 1.0 times 10 to the negative 4th, and if your exponents are the same, then you might just want to understand that they're going to cancel out, or just write them in and just do the math just to be on the safe side. So that's going to be divided by the rate from experiment 1, which is 2.5 times 10 to the negative 5th. That's going to be set equal to the concentration of nitrogen monoxide from experiment 2, which is 0.020, divided by the concentration of nitrogen monoxide in experiment 1. That's going to be raised to some exponent, which will be equal to your reaction order. When we simplify the left side, that is equal to, that is equal to 4. And then whenever we solve for the right side, that's equal to 2 raised to the nth power. So we know that n is going to, to the nth power, and we know that our exponent is going to be equal to 2. So that means that our reaction order with respect to nitrogen monoxide is going to equal 2. Now we're going to do the same thing and solve for the reaction order with respect to oxygen. Alright, so doing this, we're going to look at which reaction the concentration of oxygen changes while the concentration of nitrogen monoxide remains the same. And if we look at this, we can see that it's going to be experiment 1 and experiment 3. We're going to put experiment 3 over experiment 1 because that concentration is larger. So here we go. The rate for experiment 3 is 5.0 times 10 to the negative 5th divided by the rate from experiment 1, which is 2.5 times 10 to the negative 5th. That's going to be set equal to the concentration of oxygen in experiment 3 divided by the concentration of oxygen in experiment 1. So simplifying the left side, we've got a 2. The right side is equal to 2. Remember, that's going to be raised to the nth power. So n in this case is a lot easier to find. N is equal to 1. So over here in our rate expression, we know that that is now a 1. So now we have just answered part A and part B, which is determine the order of each reaction, or of the reactant, each reactant, and then letter B is write the rate law expression for the reaction. So we're done with that. So now we're going to calculate the rate constant, and to do that we take this rate law expression that we just determined in part B, and then we take this equation and we just substitute any of these lines into that equation. So I'm just going to use line 1, and I'm going to write those values substituted into that expression. So my rate, which is the initial rate given, is 2.5 times 10 to the negative 5th. I'm going to include my units. I prefer, instead of writing moles times liter to the negative 1, I just usually write that as molarity over seconds. That's going to equal K, which is what we're solving for, times my concentration of nitrogen monoxide, which is 0.01 squared, times the concentration of oxygen to the first power. Okay? So this is going to equal K times, 0.01 squared times 0.01 is going to equal so you're not just moving the decimal place. This is actually an exponential thing. So this is going to be times there's 5 zeros in front. 1, 2, 3, 4, 5. And then a 1. And this is going to be molarity raised to the third power. Okay, so this is molarity cubed. And that's going to be equal to what we have on the left side. So, in order to solve for K, we need to divide both sides by 0.000001 molarity cubed. Okay, which will cancel out with the right side. And on the left, something interesting happens with our units. I want you to notice that this seconds, which was in the denominator, I'm just going to move that to the denominator over here. And notice that we have molarity raised to the 1 divided by molarity to the cubed, or molarity cubed. We're going to address that in just a minute. But first we need to simplify this left side of the reaction. So when we simplify the left side of the reaction, we get 25, okay, I'm going to leave room for my units, equals K. So here's what happens to the units. You have molarity to the first divided by molarity raised to the third power, and when you divide exponents, you're really subtracting them. So that's like a 1, and then you're subtracting 3 from that, which is going to give you a -2. So this is going to be 25, and then the molarity is -2. And then seconds is still in the denominator. When you have something that is in the denominator and you don't want to write it as a fraction, you can just write it as that unit raised to the -1 power. Okay, and that's our answer for the rate constant, which I'm going to rewrite in just a second to clean up the screen. Okay, and finally we're at part D. Part D is asking us to calculate the rate at which the nitrogen and oxygen are these concentrations. So we are going to now, unless the temperature changes, your rate constant will not change. So this will be the value we substitute in to this rate law expression for this particular problem. So I'm going to take my rate, and that's what we're going to solve for. Okay, we're going to solve for this rate. Is going to equal, alright, K in this case is 25, and I'm going to leave my units out, and I'm going to explain why in just a minute. But my rate is equal to 25, and then my concentration of nitrogen monoxide is 0.015. According to my rate law expression, that's a second order reaction, so we're going to square it. And then we're going to multiply that times the concentration of oxygen, which is 0.005 raised to the first power. Alright, so when I solve for this, I get 0.000028, and I know since I'm solving for a rate, that unit is always going to be the same. It's always molarity per second, so you can write it as molarity over seconds or molarity times seconds to the -1. And that's our answer for part D. So we've now answered part D. Part E is a little bit different because it says at the instant when nitrogen monoxide is reacting at this particular rate, it's wanting to know what the rate at which oxygen and nitrogen dioxide is forming. So this is going to involve some stoichiometry, and I'm going to leave that for a separate podcast.